In section 3, we're going to learn about buoyancy. Buoyancy is the upward force that a fluid will put on an object. Now, you have experienced this firsthand, I'm sure, if you've ever gone swimming or taken a bath. You can feel the water holding your body up. That's buoyancy. And of course, you know that this is used for boats. Anything that floats on top of the water, it floats because of that buoyant force. So this slide sort of gives a derivation of where the buoyant force comes from. And I'm going to go through it briefly, but you don't need to memorize this definition. This is just for your own understanding. So here's an object that's under the water. We know at the top it's got a pressure at the top of that from the liquid, right? So the pressure at depth is in every direction. Therefore, the water is putting a pressure on the top of that based on the pressure at the top of that object. At the bottom of the object, the fluid also puts the pressure on the bottom of the object. But because we know that the pressure of a fluid increases with depth, we know the pressure at the bottom of this object is greater than the pressure at the top of this object. And it's that change in pressure that creates a larger force on the bottom than there is on the top. That gives us a net upward force of anything that's in a fluid. So I'm going to skip the algebra derivation and just tell you the buoyant force on any object in a fluid is equal to the density of that fluid times the volume of the density, the volume of the fluid that has been displaced, times gravity. So anytime an object is immersed in a fluid, it is displacing some of the fluid that would be there if the object weren't there. And that's what I mean by the volume of the displaced fluid. So this principle was discovered by Archimedes. He lived almost 2,000 years ago. And he was one of the greatest scientists that we are aware of. He was Greek. He was a mathematician, a physicist, and an engineer. He did a lot of very impressive things. And remember, this is 2,000 years ago. He calculated pi. He was one of the first. And he also learned to calculate volumes and surfaces of different shapes. Now, these are things you're often taught in grade school these days. But 2,000 years ago, they didn't know these equations. So he discovered them. And he also discovered the buoyant force. And that's why we're including him in this section. But he did more than that. He also invented catapults, levers, and screws. And again, can you imagine a world where these things don't exist? But that was his world, and he invented them. So let's go back to buoyant force for a minute. So we've got a heavy lead block and a light aluminum block. Now they're the same size, and by size they mean volume. And they're both sitting underwater. So the question is, which one of those objects has the greater buoyant force? Yeah, they both have the same volume. So if you remember, buoyant force is density of the liquid times the volume displaced times g. So if the volume displaced is the same, the buoyant force is the same on both of them. So again, here we have two blocks of identical size. One is made of lead and sits on the bottom of the water. The other is made of wood and is floating on top. Which one has the larger buoyant force? Well, this one's kind of tricky. Think carefully. Yeah, the lead block, because the one that's floating on top is not displacing the entire volume of itself, right? It's only displacing part of its volume. Part of it is sitting above the water. So the lead is displacing its full volume, while the wood is only displacing part of its volume. So the lead has a larger buoyant force. Now that may seem counterintuitive because the lead is actually under the water. So perhaps you could say that the wood seems like it has a larger buoyant force because it's floating, but it doesn't. It actually has a smaller buoyant force. So this one's kind of tricky. You have a canoe kind of barge, and it's filled with iron ore, and it's floating. So if some of the ore gets spilled or thrown overboard into the water, will the water level rise or fall? Now, so this is in a canal lock. Now, we don't have these in North Carolina, but what that is it's like a bathtub where they can control the water level. And the ship will go into the bathtub, and then they will add water or they will take away water so that the boat can be raised or lowered. And this is how the Panama Canal, for example, they will have locks, and especially in Sweden, where they can move a boat across land by having small locks. Now, the land is going uphill, so the boat will go into a lock, they'll raise the water level, and then it goes into the next lock, they close it, they raise the water level, and it goes into the next one. So it's really kind of clever, but wow. So in this case, the barge has iron ore in it, it's floating, and the ore is thrown overboard, and we're wanting to know, will the water in the lock rise or fall? Take a minute to think about it. Like I said, this one's tricky. The water level is going to fall. And the reason is because if you have a canoe, let me see if I can get so here's a small glass bowl, and you put something heavy in the canoe, it's going to sink until the volume displaced equals the weight of what's in the canoe, because then the buoyant force will be equal to weight. But if you take that and throw it overboard, of course, as you lift it, the water level is going to drop because the water's not displaced anymore. And as you throw it into the water, it's going to rise a little bit. But the easiest way to think about that is when it's in the boat, it is displacing its weight. When it's in the water, it's displacing only its volume. And since iron is heavier than water, its volume is going to be less than its weight compared to water. So the water level in the lock will actually fall because it will displace more volume floating than if it's in the water. So I'll give you a minute to read what I just said. So our next example, and this is based on real life. Archimedes developed his principle because there was a problem. The king of Syracuse had a goldsmith make an ornamental crown out of pure gold. Now, it was a crown for the wall. It was not this kind of a crown. A lot of times people will think it's this kind of a crown because he was king, but it wasn't. It was kind of a laurel decoration, a wall decoration, and it was for the temple. And so they did not want anything but the most pure and the best for the temple because you really don't want to make somebody angry, right? So he hired a goldsmith to make that decoration out of pure gold. And rumor had it that the goldsmith was cheating the king and was substituting in some other metal, like silver, for the gold. And the reason is because silver is worth less than gold. So if he can swap out, they knew how much gold was given. So whatever it was, let's say it's a kilogram, they knew that they'd given the guy a kilogram of gold, and what he's making had better be equal to a kilogram of gold. But if he swaps out some of the gold for silver, then that unscrupulous locksmith can keep the gold and line his pocket with it. So the rumor was that he was cheating the king, and so the king calls in the smartest guy around and says, how are we going to tell if it's pure gold? Because you can't tell by looking. Now, this is 2,000 years ago. Remember, screws didn't exist. So what they had to use was very, very rudimentary. So how could he determine if the crown were pure gold? Now, at this point, we know Archimedes' principle about buoyant force. And this challenges how Archimedes actually came up with that principle. So what could he do? Any ideas? If you want to think about it a minute before I press the answer, please do. So I've come up with, I shouldn't say I've come up with, there are two theories. And of course, this is 2,000 years ago, so we don't really know the answer. One answer is that you can so they come up with a lump of gold that's exactly the 1 kilogram that they gave the goldsmith. They put it in a bowl of water, and then they fill the water up to the very, very top. And then you remove the lump with the known mass, and you put it away, and then you put the object in the water. Now, silver has a different density than gold. It's less dense. Gold is very dense. It's one of the reasons that it's prized. Of course, it's a beautiful color as well, but gold is very dense. So if the crown has silver in it, when it's put into that water, that same weight will take up more space because the density is less. So if the silver takes up more space, when they put that object into the bowl of water, some of the water is going to spill out. Now, I think that that's probably what they did, because that seems like a very accurate test. You fill it up perfectly full, you put it in. If any water spills out, you know you've been cheated. But there is another way as well. The other method is to balance the weight exactly using a balance, because balances they certainly had 2,000 years ago. So if you use something, and you balance the 1 kilogram of gold here, and it exactly balances the crown or the object on the other side. And then, so this is in air. They both perfectly balance their weight. And then you take that and you put both objects into a liquid bath, for example, or 2 bowls of water. Doesn't matter. Once you put it into a liquid, then the buoyant force of those two is only going to be the same if the volume of those two are identical. So the question is the volume identical? Because if it's pure gold, the volume will be identical. But if he has swapped out any silver, just like the first method, the volume will be different. Silver, a kilogram of silver will take up more space. So then you take your balance, you put them in air, they're perfectly balanced, you dip both into water, and if one has a larger buoyant force because it has a larger volume, then you're going to see your balance is no longer balanced. Both of those methods would work, and unfortunately at this time we don't know which was used. It doesn't really matter. The big important thing is he developed his theory of buoyant force. So the first example I want to give you is here. The textbook does a variation of this problem where you know the weight of the crown in newtons, and then you're asked to calculate the density of it by weighing it in and out of water. So in air, the crown weighs 8.3 newtons. Once you dip that crown underwater, and again he's got this drawn as if it's a king's crown, but in reality it was more of a wall decoration. Once you put it in water, then the buoyant force is going to carry some of the weight. So here's our free body diagram with the tension of the string going up, the buoyant force going up, and the weight of the crown going down. And we're asked to calculate what's the density of the crown. So in air, it's just the tension and the weight. But once you put it underwater, you've got tension, the buoyant force, and the weight. And the tension in the rope is measured to be 7.81 newtons. The question is the crown pure gold? Now the way we're going to determine this is to determine the density of the crown itself. Because if we know its density, density is unique to gold. It's unique to every metal. Every metal has its own specific density, and we can use that to determine is it pure gold or not. So, where to start? So we can, if we want to know density, the first thing we're going to need to know is its mass, because density is mass divided by volume. So here's the mass of the crown. In air, it weighs 8.3 newtons. We can use F equals mg and determine the mass of that crown is 0.847 kilograms. That gives us the mass. Now if we use the buoyant force can let us calculate that object's volume, because we know the buoyant force is equal to the density of the fluid times the volume displaced times g. And in this case, the volume displaced is going to be the complete total volume of the crown itself. So by knowing the buoyant force, we can calculate the volume of the crown. And once we know the volume and the mass, then we can calculate the density of the gold the crown is made out of. Of course, we're not told the buoyant force. We're only given the tension in the string, and the weight of the crown itself is 8.3. But if we look at the free body diagram, and yes, every time you have a buoyant force, it is a force problem. That means you need to use a free body diagram, even when the free body diagram seems crazy simple compared to some of the other things we've done with forces. Very important. Include your free body diagram. It doesn't take long. It's a simple diagram. But if you don't, you're likely to get confused. So even I use the free body diagram even when I'm solving these problems for myself. It's just too easy to get confused otherwise. So with this free body diagram, you can see that the tension up plus the buoyant force up minus the weight is equal to 0 because it's not accelerating, it's motionless. So we're going to use that equation, tension up plus the buoyant force minus the weight equals 0, in order to calculate the buoyant force. So we can rewrite this equation and find that the buoyant force is equal to the weight of the crown minus the tension, because that's the only difference, right, between being weighed in air and weighed in water. The difference is going to be the buoyant force. So here we can calculate our buoyant force, and we can set that equal to the density of the water, the volume displaced, times g. So here's the density of the water, the volume is what we're looking for, times g. And from this, you can calculate the volume of that object. And it's quite small, right? So here it is, the volume of the object, and there's our mass. So once we know mass and volume, we can calculate the density of that crown. There's the mass, there's the volume. That comes to a density of 16,939 kilograms per meter cubed. Now we're not really entitled to all those sig figs, but that's okay because what we're really trying to do is compare it to the density of gold. The density of gold is 19,300. Clearly, this is much smaller than that. So yes, indeed, that unscrupulous goldsmith stole from the king. So the next topic is whether something will float or sink. So whether an object floats or sinks depends on the density of the fluid compared to the density of the object. So we'll go through this step by step. So here's an object sitting in a container of a liquid. Now we know the weight of the object is going to be down, and we know the buoyant force is going to be straight up. As I said, anytime you're dealing with a buoyant force, include the free body diagram. Even though it seems really simple, just do it. Just do it. So in this case, if it's floating, we know that the weight of the object is equal to the buoyant force because there cannot be any other forces. There's no normal force because it's not sitting on a surface. So the only two forces are the buoyant force and the weight of the object. So we're going to go through some problems in a couple of slides, but let's just see. The other thing that's on this slide I want to call your attention to is neutral buoyancy. Neutral buoyancy is when an object has the same density as the fluid around it, and it doesn't float and it doesn't sink. We'll get into this a little more, I think, on the next slide, right? So here we're going to go into it a little more. So an object will sink if its weight is bigger than the fluid it displaces. So another way of thinking about that, if the density of this object is greater than the fluid, then the weight in that volume will be bigger. So here we've got the weight of the object is greater than the weight of the fluid being displaced. And that will make it sink. That means the average density of that object is greater than the fluid. If the average density of the object is less, that means that the weight in this volume will be less than the weight of the water displaced. That means the buoyant force is going to be larger than the weight, because the buoyant force is the density of the liquid times that volume, while the weight is the density of the object times its volume. So in this case, the buoyant force is larger than the weight, and the object will tend to float up. And last but not least, is neutral buoyancy. Now, if any of you have ever been scuba diving, and I'm lucky enough to have had the opportunity to do that, the goal is neutral buoyancy. So you want your weight to exactly balance your buoyant force. And the reason when you're scuba diving is you don't want to start sinking and end up deeper than you thought. And you certainly don't want to float and have to constantly pull yourself down to see whatever it is you're looking at. So neutral buoyancy is when the buoyant force exactly equals your weight and you don't float or sink. You just sit there at one little place. So my first quantitative example I have for you is about the old cliche, oh, that's just the tip of the iceberg, meaning that's just part of the problem, right? So we're going to calculate exactly what is the tip of the iceberg. So you've got something floating, you've got this iceberg floating, a little tiny part of it is sitting above the water, but most of it's below the water. That's where the cliche comes from. Most of it is out of sight and unknown. So we're going to calculate what fraction of an iceberg is submerged. We know the density of ice is 900 kilograms per cubic meter. The density of water is 1,000 kilograms per cubic meter. Now, as I said, anytime you're dealing with a buoyant force, it's a force. We're going to draw a free body diagram. Even though it seems really simple, we're going to do it. So here's our free body diagram. We have the buoyant force pushing up and weight pushing down. And we know that this iceberg is not accelerating, it's just sitting there floating. That means that it's in equilibrium and the net force is zero. So the buoyant force upward minus the weight is going to equal to zero. Now we know what the buoyant force is. We have rho GD for that. I think I said that wrong. Rho times V times G for the buoyant force. And we know the weight is mass times gravity, but we're not given the mass of the iceberg. So in order to try to figure out what the mass of the iceberg is, I'm going to use this relationship that the density of the ice is equal to the mass of the ice divided by volume. And the reason for that, instead of using just M, is we're wanting to know the fraction submerged. So we're going to need to have the mass in terms of its volume. So once we use this relationship, we can then substitute in for those two forces. So here's the buoyant force, density of the water times the volume of the iceberg that's submerged times G minus the weight. So here's the mass of the iceberg, right? I rewrote this. So the mass is density times volume. Density of the ice times the volume of the ice. Now this is the total volume of the ice, where this is just the volume that's submerged, times G. And we know that those two forces net out to zero. So from here we can take this equation and simplify it a little, because you can see that both terms have G in it, so we can cancel the G and we can rewrite this equation so that we've got the density of the water times the volume submerged is equal to the density of the ice times the volume, the total volume of the ice. But what we're looking for is the ratio. We're looking for the fraction that's submerged. So we're going to want the volume submerged divided by the total volume. That's going to be the fraction of the iceberg that's submerged. So we're going to rewrite this equation so that one side is going to be V submerged divided by V ice. Now that's very straightforward to do. We just bring the ice here and we bring the water to the other side, and you find that the volume of the submerged, the ratio or the fraction of the volumes, is equal to the ratio of the densities. In this case, we've got the total volume submerged is equal to the density of the ice divided by the density of water. And in this case, since it's 90 and 1,000, this ratio is 90%. The density of ice is 90% the density of water. That means the iceberg will be 90% submerged. Now this relationship will hold for any floating object. Only floating objects, because we started with the buoyant force being equal to weight. So the fraction of any floating object that's submerged is equal to the ratio of the densities. And remember, the floating object has a density that's less than water. So my next quick check for you, is we have 3 blocks here. They're sitting in the water. And you can see that the amount that they're in the water and the amount above the water varies. So which one of these blocks is the most dense? Did you get that? Right, so block A is more submerged in the water. Since it has a larger fraction submerged in the water, we know that its density is greater than the other blocks. This one looks like it's about 50-50. This one looks like it's 2/3 out of the water. So the larger the density, the deeper an object will float. And we saw from our last example that it is exactly the ratio. So the ratio, the percent of this object that's out of the water will be exactly, submerged in the water, will be exactly equal to the ratio of the densities to the liquid. So here's my next example. We've got a block here and it's sitting in water. When it's in water, it's got a submerged depth of 5.8 centimeters. When you take that same block and you put it in an unknown liquid, it only floats with 4.6 centimeters being submerged. So the question is, what's the liquid's density? Now I'll give you this example because there are such a things as calibrated density floats, and you can use these, as long as they're inert, to put them in unknown liquids, and you can readily identify the liquid by knowing its density. So we're going to do the math for this. So here we're told that the cube is 10 centimeters, each side is 10 centimeters, and it's submerged in the unknown 4.6 centimeters, and the known liquid is 5.8. We're going to calculate what's the density of that unknown liquid. Now you might be tempted to jump straight to that ratio rule. You can certainly do that. The way I do this here is I say that the weight of this block is the same in both cases. So my next problem has the same cube floating in water, floats to a depth of 5.8 centimeters, but in an unknown liquid it floats to a depth of 4.6 centimeters. And we're asked, what's the liquid's density? Now this is an interesting problem because it's very common that you'll actually use density blocks to calculate the density of an unknown liquid. And if you've ever brewed beer or wine, you know that there's a little tool they sell that you float it in your beer or wine as it's brewing, and you can determine the alcohol content by measuring the density of your liquid as that sugar water, which is heavy, converts to alcohol, which is light. So this is a very practical example to go through, and I'm going to do this problem two ways. The first way is to use the ratio of the volumes and the ratio of the densities that we just did with the tip of the iceberg example, and then the second way will be to use the buoyant force. So in this problem, I'm going to use ratios. So we know that as the block is floating in the water, the ratio of the density of the block to the ratio of the density of the water is going to be the same as the ratio of the volume submerged. So that's going to look like this. So in the water, we know that the fraction of the block that's submerged, that's going to be 58 centimeters out of 10. That's 0.58 or 58%. We know that the fraction submerged is equal to the ratio of the densities. Using this, we can calculate the density of the block. Right, so we've got 0.58 is equal to the density of the block divided by the density of water, which is known. So we can calculate that the density of the block is 580 kilograms per meters cubed. Then we can use this density over here in the unknown liquid. We know those ratios still hold. So once we know the density of the block, then we can look at the situation over here in the unknown liquid, and we know that those ratios still hold. So when it's in the unknown liquid, we know that the volume submerged divided by the total volume of the block, that's 4.6 centimeters out of 10, so that's 0.46 or 46%. That's going to be equal to the ratio between the density of the block and the density of the liquid. This time we know the density of the block, so we can calculate the density of the liquid. So here's what we know, 0.46, density of the block divided by the density of the liquid, so we can determine that the density of the liquid is 1260 kilograms per meter cubed. Round that off to 13 kilograms per meters cubed. Now there's another way to do this problem, And although this is, I think, a little more direct and simpler, I'd like to show you the other method just so you get a chance to see it. This time we're going to solve this problem using the buoyant force. So in both cases we have the weight down and the buoyant force up. I don't have space to draw that free body diagram, so I'm just going to talk you through it. So here the weight down, the buoyant force up, the weight down and the buoyant force up. Since it's floating, in both cases we know that the buoyant force is equal to the weight. Since the weight of the block is the same, it's the same block, we know that in both cases the buoyant force is equal. So I'm going to set, we know also that the buoyant force is the density of the fluid times the volume of the fluid that is displaced times g. So I'm going to set those two buoyant forces equal to each other. So here we've got the density of the liquid times the volume of the liquid times g is equal to the density of the water times the volume of the water displaced times g. Now, as you can see, we've got g on both sides there. So we can cancel the g. But we also need to calculate the volume of the water displaced. So here we can see that that's a rectangular shape. So it's going to be depth times length times width. And in both cases it's a 10 by 10 centimeter block. So the displacement is going to, the displaced volume is going to be this depth times 10 centimeters times 10 centimeters, which is the depth times 0.1 meters times 0.1 meters. And that's in both cases. So I'm going to go ahead and substitute that in. So here we've got the density of the unknown liquid. There's its depth in meters times its width and length. Here's the buoyant force on the water, from the water, the density of the water, the depth in water times length and width, again times g. And you can see here that both the g cancels and most of this cancels, but I think I've got them multiplied out. So here, multiplying this out, the 0.1 cancels and the 0.1 cancels. So here we can solve for the density of the liquid. It's just 1,000 times 0.058, divide by the 0.46, and again the g and the 0.1s cancel. So that gives us a density of 1260 kilograms per meters cubed. Notice that's the same answer, so it doesn't really matter how you do this problem. You can use the ratio because it's floating, and again that ratio problem only works when it's floating, or you can use buoyant force. Either way should give you exactly the same answer. So of course we can't do anything about floating without talking about boats and balloons. So in this first drawing, we've got the hull of a boat. Now the boats are hollow, so this outside shell can be very strong, and you know, like we saw in the original picture, you can make this out of concrete. Because the boat is hollow, it ends up displacing a very large volume. So the weight of the actual hull itself doesn't matter much, as long as it displaces a volume large enough to carry its weight. And what is also interesting about this, you can see that if you're going on a canoe trip or you're getting in the canoe will be pretty high in the water, and as you add weight, the boat will sink until the weight of the canoe and everything in it exactly matches the volume, the buoyant force from the volume of the displaced water. So as you add more weight to a canoe, it sinks so that it can displace more water and have a larger buoyant force. Hot air balloons are very similar. You've got a buoyant force upward and a weight downward, and the way hot air balloons work, as I'm sure you know, is you heat the air in the hot air balloon and hot air expands. So it will be less dense than cold air, and as it's less dense, it takes up more space for the same weight. Actually, some of that air is going to be coming out of the bottom. As it expands, some of the mass comes out of the bottom of the balloon, so the balloon carries less mass. The air inside the balloon has less mass, so that the buoyant force ends up being larger than the weight of the balloon, and the balloon will go up. So here I've got another quick check for you. We have 3 blocks. They're all underwater. Block A weighs 50 grams, Block B weighs 40 grams, and Block C weighs 50 grams. We're told they're all the same size. And when you're asked, which one has the largest buoyant force? What do you think? They all have the same buoyant force. Although the net force may be different because they have different masses, the buoyant force is just the density of the liquid times the volume of the liquid displaced times g. Now the density of the liquid is the same. The volume, we're told they are all the same size. So the volume of all three of these are the same. That means they're all going to have the same buoyant force. So this one's a little different. Here we've got those blocks hanging from a scale. And in this case, we're not asked for the buoyant force. We're asked for the reading on the scale. So here we're sort of going to need to think a little bit about the free body diagram before you answer. Give it a thought for a minute and see what you think. Is that what you came up with? So here we've got weight being pulled down, and in this case, these A and B have the same weight, where C has more weight downward. The buoyant force on all three of these are the same. So the net force on this one is going to be downward more than the net force on these. Of course, they all have tension upward. So in each case, the tension is going to be equal to the weight minus the buoyant force, because tension plus buoyant force minus weight equals 0. So the scale is going to read the weight minus the buoyant force. So here, these two, the weights are the same. This one has more weight. In all three cases, the buoyant force is the same. So that means the scale will read more for this one, and the other two will read the same. So here I've got one more problem for you. Here we've got a hot air balloon. We're told it has a volume of 2,500 cubic meters, and it's in Fort Collins, Colorado, where the density of air is 1.0 kilograms per meter cubed. First off, we're asked to calculate what is the mass of the air that the balloon displaces. We'll just do these one at a time. So for part A, if we know the volume and we know the density of the air, then we can calculate that mass using the relationship that density is equal to mass divided by volume. Rewriting that, we know that mass is equal to density times volume. So we can substitute in what we know. There's the density of the air, there's the volume of the hot air balloon, and we can conclude that the mass is equal to 2,500 kilograms. So for part B, it says if heated to the maximum temperature, the air inside has a density of 0.8. What is the mass of the air inside the balloon? So again, if we know density, we know volume, we'll use that same equation. The mass of the hot air balloon is 0.8 times 2,500. That means the mass of the air inside the hot air balloon is 2,000 kilograms. So then the last question asks, how much mass can the balloon lift? So then we really sort of need a free body diagram, but I don't think I have room for it. But you can imagine we have a buoyant force upward, the weight downward, and then we're going to want to lift it. So this is the lifting force. What is the force that the balloon can lift? So the weight and what it's lifting is going to pull the balloon down, and the buoyant force is going to be pulling the balloon up. So we know that in order for it to accelerate upward, it's going to have a net force. If it's going very slowly, maybe not, it's not accelerating, it's just barely moving upward, and we can set them equal. But that buoyant force has to be at least equal to the weight minus the lift. So we can calculate the buoyant force, we can calculate the weight, and we're asked for how much mass. So the force that it can lift is just going to be the mass it can lift times gravity. So solving for the force of the lift, we get the force of the lift, moving it to this other side, and then I've flipped my equation. The force of the lift has got to be less than or equal to the difference between the buoyant force and the weight. So we know that the buoyant force is the weight of the displaced fluid, right? So the buoyant force is the density of the fluid times the volume of the fluid times g. That's just the weight of the displaced fluid. So if we substitute in what we know, mass that you're wanting to lift times g is going to be less than or equal to the mass of the air in the air that the balloon displaces. That's the mass of the cold air times g minus the mass of the hot air times g. So we know all of these values, and you can calculate what the mass is that can be lifted by simply the difference in the mass of the cold air and the mass of the hot air. So that means this balloon is going to be able to lift about 500 kilograms. So we also know that our bodies are made of, bones. Bones are pretty dense. Fat floats. We've always heard that. The overall density of the human body is about 1050. And yeah, so if you're swimming, if you're an experienced swimmer, that if you blow all of the air out of your lungs, you can sink to the bottom of the pool. If you take a nice big deep breath, you can float pretty easily. So the air in our lungs is expanding the volume. So this is pretty close to the density of water. So if you get a big lung full of air, that means your volume is increased and your density will decrease and you can float. So the fish has a very similar thing called a swim bladder, where it can fill that bladder up with air and float, or it can expel the air out of that swim bladder and sink. So this slide is just giving you a little bit of an introduction to what's going on in our next problem. We're told that a yellowfin tuna with its swim bladder deflated, that's similar to a human with all the air blown out of its lungs. It has a density of 1050. And we're told it's swimming near the top of the ocean, and we're asked to find out what volume of gas is needed so that it can have neutral buoyancy at the top of the ocean. Now remember, neutral buoyancy is when the object's buoyancy equals the density, the object's density equals the density of the liquid around it. In this case, the density of seawater is 1030. So with the swim bladder empty, the fish has a density of 1050. With the swim bladder full, the fish has a density of 1030. Now we know the mass of the fish, so it should be pretty easy to figure out the change in volumes, right? You know mass and you know density. Here we know mass and density, so we're just going to calculate the volume of the fish in both cases. Right, so as I said, neutral buoyancy is when the fish density equals that of the water, 1030. And we know the mass of the fish, so we need to find his volume. So if his volume, the density of the fish, we want the density of the fish to be equal to the seawater when he's neutrally buoyant, and that's going to be equal to the mass of the fish divided by the volume that his body needs to have. So we'll start with what's the volume that the fish needs to have in order to be neutrally buoyant. So we'll substitute in the volume of the seawater, the mass of the fish, and that can be used to find the volume that the fish needs his body to be. So that means his volume that his body needs to be is 0.0092. We take his mass, divide by the density, and we get that volume. That's how big the fish has to make his body in order to be neutrally buoyant. And we're going to take that and compare it to the initial volume of his body. So when he's deflated, we know his density is just equal to his mass divided by his deflated volume. And we can use this relationship to calculate his deflated volume. So here we've got his uninflated density is equal to his mass divided by his deflated volume. And we can calculate his deflated volume, again, by taking his mass divided by density. And we find that when his air bladder is completely deflated, his volume is 0.00905. Looking at comparing these two, when he's deflated, you can see that he needs to inflate by about 0.007 meters cubed. And I thought I had a percentage on there, but I don't. So that's how much he needs to inflate his swim bladder by. So he's, when he's normally about 905, he has to inflate it, what is that, about 2 parts out of 9, about 20%, in order to be able to be neutrally buoyant. So the good news is that's the end of this section. The key concepts for this section, and if you noticed, this section was about half of what we did for the entire chapter. We covered Archimedes' principle, and that said that the buoyant force on an object is equal to the weight of the fluid that the object displaces. In equation form, the buoyant force is equal to the density of the fluid times the volume of the fluid displaced times g. Whenever you're dealing with buoyant forces, please draw the free body diagram. Even though it's simple, please draw it. It will help you. And again, if something's floating, there is no normal force. It's just the buoyant force up and weight. If it's sitting on the bottom of the ocean, if it's on that surface of the bottom of the ocean, then it would have a normal force. But if it's floating, it does not. Also, we learned that if an object is floating, the percent of the object that's below the liquid is simply equal to the ratio of the densities. Once we've derived that, you can use it. And that's it for this chapter.